Excellent. Thank you so much, Sam. I really appreciate this opportunity. Sam mentioned I'm one of the co-founders and chief technology officer here at ReFirm Labs. And hopefully you guys can learn a little bit today about analysis of real-time operating systems, specifically analysis of the eCos operating system. And just a little backstory on sort of how this talk came to be. We were, as probably many people on the stream realize, is that there was a vulnerability released about in January that affected pretty much every single cable modem almost in existence, right? Pretty much every cable modem based on the Broadcom chipset. And so we kind of wanted a way to automate the identification of that using just the firmware image itself. So there was some existing capability to identify this vulnerability by active network interrogation, but we're a firmware analysis company, so we wanted to take a different approach, sort of get more to the ground truth. So I have a few slides, and then we'll just jump into GHIDRA and take a look at some disassembly. So just a little bit of background on eCos. Depending on how much firmware you've looked at from a vulnerability analysis point of view, you may be familiar with it, you may not be familiar with it, but it's an example of a real-time operating system. And basically what that means is you traditionally when you're doing vulnerability analysis, you have either like an ELF file or a PE file, and this file tells you, hey, we have code here, we have data here, my CPU architecture is this. But in RTOS land, you sort of get none of that, right? You get a flat memory model, right? You can kind of think of it as everything on the device is running in kernel space, right? There's no user space, kernel space separation. There's no context switching. There's no moving pages back and forth. You only operate in that kernel space. And there's benefits and detriments to that, right? The benefit of running solely in kernel space is you have direct access to the hardware. You can do things very quickly. And the benefit of real-time operating system is that you can do real-time operations, right? You don't have to worry about potentially getting context switched when you're in the middle of a critical operation. But the detriment is that you really don't take advantage of any of the sort of modern security mitigations that have been around in the last decade, right? You generally don't get stack protection. You generally don't get sort of no execute pages, things of that nature. And so when a vulnerability, especially a remote code execution vulnerability, pops up inside of an RTOS, you have full unfettered control over that device, right? So it's a very dangerous set of circumstances that would lead you to be able to control, like in this case it's a cable modem, but you can this stuff is being used in industrial control and other medical device fields and things that are much more sort of life critical. And so from a vulnerability analyst point of view, we need to answer a few questions. First we need a firmware image, right, to do that analysis on. And we need to figure out what the CPU type is. And sometimes that's really obvious and sometimes it's really not. We need to figure out where the load address is for that firmware image, right? A lot of people, when they first start doing analysis on real-time operating systems, they assume that the RTOS is going to be loaded at sort of the CPU initial instruction address, right? So MIPS and ARM, they have a fairly standardized set of addresses that they're going to start execution at. However, even in this small embedded RTOS world, we still have a bootloader involved, right? And the bootloader is generally there to recover an image in case of a bad flash, but it's also responsible for finding the image of the RTOS and loading it at a specific address and jumping to it. And so there is no, while each RTOS themselves have a standard load address you can generally rely on, generally that changes between RTOSs and even between CPU architectures within single RTOS. And then you also need to figure out, because this is one large monolithic kernel, we need to be able to figure out where code starts, where code ends, where data starts, and where data ends. Because we don't want our disassembler to be interpreting data as code or code as data, right? And in this specific case, because we're dealing with a MIPS device, we need to be able to figure out what the global pointer register value is, and that allows us to make more intelligent decisions on how these long far calls might be being made. It's also useful to look at the CABLEHAUNT vulnerability itself. So these are just snippets taken from the report that was published on CABLEHAUNT.com. But you can see the vulnerability is pretty straightforward. You put a malicious buffer in a parameter called fstart hz or fstart hertz, and it causes a buffer overflow. And so you can see that this is the cable modem is implementing a spectrum analyzer web interface that was designed for the carrier to be able to detect like poor signal quality and other signal impediments on CPE equipment or user premise equipment. And it was never intended for example, for end users to access this, right? But it was all implemented in WebSocket API calls with JSON back and forth, right? So it's a very sort of modern web technology being implemented in an RTOS that was first implemented 21 years ago, right? And so that's sort of wrought with peril, right? Like if you took a traditional Linux developer and told them that you were gonna parse user data in JSON format in the kernel, they'd probably look at you kind of strangely. And so that's exactly what's happening here, right? You have these JSON blobs going back and forth from effectively kernel space on this device. And so when this bug came out, we went to our nearest Best Buy, and we picked up the cheapest cable modem that we could find there, right? I think it was like $100. And it comes, it's DOCSIS 3.0. It works on Comcast and Charter and all these other networks, right? And so we went down the path of, can we tell our users if CABLEHAUNT is affected in this particular firmware image, right? And so the first thing we did, we took the device home, we took it apart, right? We didn't even turn it on, and we connected our C232 FTDI cable to the UART on the board. And lo and behold, we turn it on and we see all sorts of useful stuff, right? So the most important thing we saw was that in the image in the bottom left here, which tells us the exact load address that the eCos image is being loaded at. It also tells us that the eCos image is 14.5 megabytes, which is just crazy big for an RTOS image, in my opinion. But we also got, and it's not shown here, but we also got a full Linux command line interface, right? So we knew that there was eCos on this device because we see it in the boot log, right? But yet we're getting a Linux prompt when the device fully boots up. And so as it turns out, there's two effectively firmwares running on this device. There's an entire eCos subsystem, which is just for the cable modem itself, and then the Linux subsystem, which is what like the end user would interact with, like setting your DHCP settings and things of that nature. You'd be interacting with the Linux side. And so you have a Linux router, wireless access point, things like that, and then you have the modem. And there's a very sort of good reason why those two distinct things are separate, right? Because in the cable operator world, the cable operators are the one that have complete control over the image that runs on the cable modem itself, right? So if either you rent a device from your provider or you buy one at like Best Buy, for example, you plug it into the cable provider network, they are the ones that control the firmware that's running on the consumer premise equipment or the actual cable modem. And so they're able to push updates, they can change configs, they can do effectively whatever they want to that end user's modem. And so keeping the Linux subsystem, which is sort of like the user control part, and the eCos subsystem, which is sort of like the carrier control part separate, is actually a pretty good design. But the downside is that you can't just go to like manufacturer websites, grab a firmware, and see what's inside that eCos image, because it's all controlled by the carrier. So what we were able to do, because we can't get access to that firmware image by just downloading the firmware for the device, what we did is we got the shell into the Linux subsystem. We figured out how to fire up a telnet daemon and then exfil the firmware by effectively DDing the MTD block device that stored the eCos firmware image. Right? So now we have the load address for the RTOS. Right, we have the firmware image itself. You can see that in the bottom right, Binwalk is telling us that it's MIPS, which means it's not MIPS EL, so that means it's going to be MIPS big endian. So, I've been using IDA for probably 15 years now. So, I'm very comfortable with it. So my next step would logically be, hey, let's throw this into IDA. Right? But loading RTOSes in IDA is kind of wrought with peril, right? So you tell IDA, hey, we have a MIPS big endian system. You tell IDA, hey, we have this load address where the image is being loaded, but the result is that we get no cross references, right? So IDA is easily able to identify like function boundaries. It's easily able to traverse the code tree and find new functions and find cross references between those functions, but the data cross references just don't work. Right? And that's what we want to find. We want to find where the vulnerability is within this firmware. And so loading an RTOS in IDA in reality involves defining the CPU architecture, defining the load address, doing some disassembly manually, right, to identify what the global pointer value is, telling IDA what the global pointer value should be, then doing some more manual analysis to say, where does my code end and where does my data start? Then tell IDA where code ends and data starts. Then going to the interweb and finding a GitHub repo from Craig Hefner saying, this is the Codatify plugin that allows you to fix up the data section to define strings and words and things of that nature. And then turn on auto analysis and then wait, a few minutes, and you might get cross references that you're interested in, right? So in this case, this is an example. We went through the process of loading into IDA, but at the end of the day, you're still stuck with, disassembly, right? And there's no symbols in this particular firmware image. So you're stuck with identifying leaf functions and then trying to name them just by looking at MIPS disassembly. So we decided to take a different path and just try out GHIDRA. It's the brand new hotness everyone is getting on board with. So let's see how GHIDRA handles RTOS loading. So we have we just tell GHIDRA, hey, we have a MIPS big endian 32-bit CPU. We tell it, here's your base address. Now let's see, I'm gonna pop GHIDRA hopefully into the screen here. And this is what we get, right? Now, granted, I didn't load it live for you on this video because it takes like probably 15 minutes to load this 14 meg image into GHIDRA. But the sort of most important thing is that we can go into our defined strings window here, right? We can look for our parameter that we're interested in finding the overflow for, double click it, and we see instantly we have one cross-reference, right? So we can click on that, go to our decompiler, and instantly we can sort of see the vulnerability. Now, I cheated a little bit, right? Because I took the firmware image that was released as part of the disclosure document and was able to name functions, right? So I took the other image, I think it was a Technicolor device, I took that eCos image, and based on the report, I was able to name certain functions, and then I created a function ID database, right? So I created my own custom. I called it CABLEHAUNT.FIDB. But what this allowed us to do is when we loaded this image, we got the string, the functions named for us right off the bat, right? And so when you look at this now, right, the vulnerability is fairly obvious, right? Especially looking at the decompilation. We have our fstart hurt string here. We have a call to stir. ivar1 is likely that JSON blob that's being sent in the WebSocket. And we check to see if we have a value, right? And if we do have a value, we look for 0x2c's comma, right? So we're looking for a comma within after ivar2 inside of the ivar1 blob. And then we use strncopy, right? And when I first saw this, I was like, well, they're using strncopy. Like, why is this an overflow? Until you realize that they're passing the wrong size into strncopy. They're effectively taking the length between the end of fstart hurts and the beginning of that comma and passing that to strncopy. So even though we have a 24-byte stack variable here, it doesn't matter. The length of that variable is completely ignored, and we have this is where the overflow is. And so and then they take that value, convert it to an integer, and use that as ivar8, right? But what's interesting is that we can see that the same exact parsing logic is used for fstop hurts and FFT size and num of samples. And so I haven't verified this, but I can pretty much almost guarantee that there's an overflow in every single one of these variables. And so what we really want to demonstrate here is that the time it took to go from extraction of the firmware image to being able to identify and then automate the detection of this CABLEHAUNT within an eCos image was greatly accelerated based on the fact of how GHIDRA is able to automatically identify the string cross-references and the demarcation between data and code, as well as just being able to look at decompilation, right? And so because you can look, I actually checked out the CVS from the CVS repository. You can go to the eCos website and you can check out their full source code repository using CVS, which I haven't used since 2005. And when you look at that code, you can actually almost line for line make a correlation between these library functions and the original C source code. It's actually that good, right? So identifying those leaf functions, those library functions, should be fairly straightforward using the eCos published source code from 11 years ago as a good reference, which is good and bad. It's good because there's source code that we can look at to try and identify the API calls, right? But it's bad that the code hasn't changed that much in 11 years that it's pretty easily identifiable. One other interesting thing I just want to demonstrate is that this isn't the only real use of string copy in this image, right? So you can go here and you can look, and there's GHIDRA's not working. Oh, here we go. So there's 71 other uses of strncopy. Similarly, there's 63 references just to plain old, good old fashioned stir copy. So I guess the lesson here that we kind of want to convey is don't parse JSON manually in kernel space, and try to maybe try different tooling. If you're used to using IDA Pro, give GHIDRA a shot and see what it can do. It certainly surprised me, and it might surprise you as well. That's all I have for today. Thank you so much for listening. I did finish a bit early, If you guys want to maybe pop some questions into Discord, I'm happy to discuss this further with you guys.
We think about IoT Village as a movement. These devices are being adopted so rapidly that security is not effectively being baked into the development and deployment of those solutions. That puts consumers at risk, that puts businesses at risk, that puts governments at risk. And what we're trying to do is to galvanize a community around solving that problem.
Every time somebody hears IoT, they immediately think, I don't want this in my house. But as time goes by, that choice of having something in your house or not is not really there.
You can walk in the village, you won't feel like you're asking a dumb question, and you'll still walk away learning something no matter what your skill level is or knowledge.
IoT Village provides an opportunity for people to experience security in a very tangible, very real way.
So what ends up happening is, I can kill Lisa right now. She's being smothered. She's flatlining, patient monitor's going nuts, she's dead. What's going on at the nurse's station? She's fine. What I'm doing right now is we are replaying recorded data of a healthy patient. So this patient monitor is something you'd see in every hospital room in America probably. The IoT Village seeks to raise awareness of IoT security. We want consumers to be able to make informed decisions, and we want manufacturers to improve their security.
So we put a lot of work into the security on the Bird 2, and we wanted to put it in front of the DEFCON community and see what people were able to do with it. We've learned stuff about our tech that we didn't previously know, and from my perspective, that's phenomenal because we have a really talented team internally, but when we can be educated by people external to the company, it's a big, big win.
We really want to show that we very much welcome the work that security researchers do, and even though we work in a world, the medical device world, that's not as accessible to the people that work in this space, we really value the input that researchers have. We want to show that we love for them to work with us on medical devices and what they can find in it.
Security is a mission-critical part of being a pioneer. And by participating in this, they're able to address some of the challenges that are introduced through innovation.
Building a contest to challenge hackers, at the world's biggest hacker conference, if these guys didn't know what they were doing, this room would be empty.
So IoT Village is awesome. Unfortunately, like a lot of hackers work in these small groups, they don't really share a lot of information because they kind of want to monetize or capitalize off of the information that they have. So being here in IoT Village gives us an opportunity to talk to a bunch of other hackers that we wouldn't normally talk to and share information and kind of like come together as one.
I think it is the best thing since sliced bread, personally. This year we're here at DEFCON helping run a hands-on lab, IoT Hacking 101. How do we get people involved with this? Because it might be intimidating, right? Walking up into a big CTF at a big conference. The idea is that we handhold them all the way through from the basics of firmware analysis right through to discovering a bug and popping a device or two.
I just connected over Netcat. There was nothing fancy, no authentication, anything like that. And this number here is your authentication token. It's a serial number on the device. That's what they're using for authentication. So what we're doing is that we're showing people how we find vulnerabilities in embedded devices. Specifically, I've been targeting NAS devices, and I've been showing how we find vulnerabilities, develop an exploit for it, and exploit it from the attacker's perspective.
IoT Village is the face of IoT security worldwide. They're probably the most preeminent brand when it comes to dealing with IoT security. We have expertise, they have expertise, and we feel that it's more than just a sponsorship, it's more of a partnership in which we share stuff with each other. The visibility that you get from all of these conferences is an amazing thing.
It's only going to get more and more relevant, and the devices are only going to get more and more prevalent. And so I think it's just a great interactive, hands-on experience for people to come and get immersed.
We know that these security challenges that are inherent within connected devices, they're not going away on their own. We're able to make these challenges come alive, to become real, to be tangible. And when we do that, we enable people to participate in being part of the solution.